No, I'm going to grade it. I'm going to have to look at like the whole class before I assign a final grade to it, you know. Okay, so 6.2 is now in the past. And not to say that you're not going to see it again, but we move on, right? And, you know, one of the things I hope I've stressed to you about this class is that, like, the train keeps moving, you know, like, regardless. It just keeps moving. And it really does not slow down, you know, ever. So, and I would even argue that it speeds up a little bit in Chapter 8 because it's harder material. So, you know, the pace that we're setting here, I hope you've kind of gotten used to, like, this is the ride I'm on, okay? All right, so 6.3, partial fractions. We start to bring a lot of ideas together here. Stuff from college algebra, partial fractions. You did that either in college algebra or pre-cal. And here's where we're going to use it. We're actually going to use it to find antiderivatives. But before we can actually begin doing it, we need to get a lot of things out of the way first. Okay, so we should all be comfortable with Formula 17. That's on your formula sheets, right? You're allowed to have that formula. We first saw this in this form. Well, that's a good marker. When I first introduced you to that, I said, you know, that's one that you should put a star next to. You're going to see that a lot, right? Remember that? And we said that the antiderivative of that was arctan x plus c. And that is this formula, right? Except that instead of u, we have x, right? Because that's the variable. And then for this particular example, a here is 1. So notice that in the general formula, you actually have a 1 over a out front, and inside the argument you have the variable over a. So if I were to change this problem to, let's say, 4 here, right? 1 over 4 plus x squared, then this is no longer correct, right? I would need to put what in front? 1 half, 1 over a, and then inside the argument of the arctan I would need what? X over 2, okay? So the main idea here is this. If we have anything of this form, we can go straight to the formula, all right? So if we're working through a problem later on, and we ever see something like that, we're going to be like, okay, good, Formula 17, right? Now, it's going to take work to get to there, but if we see it, we're going to be relieved, yes? Okay, so let's look at some other things that we should be able to handle at this point. So let's start with this one. If we ever see an integral where we have a constant in the numerator and a linear expression in the variable on the bottom. So everyone agrees 2 is a constant. Everyone agrees that x minus 4 is a linear expression in x. So if we ever see that, we're in business. This should not require much work at all from us. We could take that constant out, right, like that. And then we could do just a basic u sub. What would the u sub be here? X minus 4, du is dx, and then this integral becomes 2 integral 1 over u du, right? And then the antiderivative of that is 2 natural log absolute value of u plus c, and switch u back to what it was, and we're done, right? Now, what you want to get to, okay, where you want to be at very soon, like this week, is that you don't have to write anything down to do this problem. You want to be able to look at that and be like, okay, I realize that the 2 is just a constant that comes for the ride, and that the denominator, because it's linear, the derivative will always be a constant, won't it? Like in this case, what's the derivative of the bottom? 1 dx, right? So because of that, I know I'm going to have natural log here. It's just a matter of making sure that I take care of any scaling that needs to be done. I'll show you in a different example, but let me see what my next one is. Yeah, like look at this one. Okay, so we have a constant on top, linear expression on the bottom. So because it's a linear expression on the bottom, I already know, well, because it's constant on top and linear on the bottom, I already know my answer is going to involve a natural log. Okay? This is a linear expression, not a linear expression squared, not a linear expression under a square root, just a linear expression by itself. If that happens, then we know it's natural log. But we have a little bit of a problem on this one. What's the issue? That -5 in front, right? That -5. Because if I let u be the bottom, what's the derivative? -5, right? dx. And I don't have a -5 dx, so I would have to scale both sides, wouldn't I? So I'm going to try and do this without writing anything down. Okay, I'm going to see if I can just get to the answer without writing any work, any u substitution. I know my answer is natural log of 4x minus 5, 4 minus 5x plus c, but I need to scale this by something. What do I need to scale it by? -1/5. Now, on a test, could you use u substitution? Absolutely. What's going to be the drawback to that? Time, okay? Time. So you want to get to the point where you just look at that and go straight to the answer. Any questions on that? Sure? Now's the time? No? Okay. So we should be able to handle constant over linear, no problems at all. We're good to go. All right? What if we have a constant with a linear expression in the bottom, but it's repeated? Repeated meaning I have a power other than 1 here. Maybe it's squared, maybe it's cubed, maybe it's to the 5th power. Well, what I can tell then is that it's not going to be a natural log, because the natural log only works if the bottom was like something to the 1st power, right? So let's work through this one by hand, and then let's see if we could have done it without actually having to write that much down. So right now, I'm going to make a u substitution. U is going to be 2x plus 1. du is 2dx, right? I don't have 2dx. So I scale both sides by 1/2. And then I rewrite everything, right? So my new integral becomes integral. I have a 1/2 out front that comes from the 1/2 du. And then what? 1 over u squared, right? 1 over u squared. I'm not going to write it that way. I'm going to write it u to the -2. The reason I'm going to write it u to the -2 is because I'm going to be using the power rule to take the antiderivative. And then du, right? That's what I have. So the antiderivative of that should be 1/2 times, now you have to run your power rule on that. So you get what? -1 times u to the -1 plus a constant. And that turns out at the end to be -1/2 u to the -1 plus c. What's u? 2x plus 1. So could I write it this way? -1 over 2 times 2x plus 1 plus a constant. That's just me taking my u and dropping it back down as u to the 1st power on the bottom. And then there's my u, -1/2, yes? Okay, so could we have done this without writing anything down? I think yes, but it depends on where you are, okay? I mean, like, you really have to be comfortable with the power rule mentally to be able to do this without writing anything down. So if we go back and kind of look at it again, we say, all right, we have a constant over a linear expression to the 2nd power. So I know that this is going to be a basic u substitution. I know I'm going to have to scale by 1/2, right? So I'm writing down what I'm thinking here. So I know my answer. I'm going to have 1/2 there to scale out that 2 in front, right? And then I'm thinking to myself, I've got 1 over u squared, which is u to the -2. The antiderivative of that is -1, right? U, which is 2x plus 1 to the -1 plus c. And that's the same answer, right? Okay, so like I said, you want to try and get to this point. I know it's not realistic for everyone to get to this point right now. You always have this, but like I said, time, right? Time is something that's valuable to us on a test. All right. How about this? Let's see if we can't work through this one. This is the same format, isn't it? A constant over a repeated linear factor. So for this, let's see if we can do it without any sort of writing down any U substitutions. Do you have to scale? No. You don't, because there's a 1 in front, right, of the x. So you don't have to scale by anything. All right? This really looks like a 1 over u cubed, right? Which is u to the negative 3. So what's the antiderivative of u to the negative 3? Negative 1/2 u to the negative 2. But what's u for us? X minus 5 to the negative 2 plus c. I know that's a lot, but you know, so we're trying to be able to process all this. You all right? Yep. Okay. Sure, no objections? You can object, it's not going to change the fact we still have to do it, but yeah. All right, let's change it up. What if we have a constant over a quadratic, right? This is the first time we've had this. A constant over a quadratic, but there's something special about this quadratic. There's no x term. What I mean is we have an x squared term, right? We have a constant term, but we don't have a single x to the first power term, right? And we have addition between these two things on the bottom. So we have an x squared term, we have a constant term, and we have addition between them. We should be able to handle that. How do we handle that?
Trig sub.
Ooh, yeah, you could do trig sub. But can you do it without any work?
Formula 17.
Formula 17. This is formula 17, right?
Yeah.
This is basically like 1 over variable squared plus constant squared. And the antiderivative of that should be 1 over a arctan of u over a, right? So for us, we're going to have, what's a? 3, so it should be 1 over a, 1/3, arctan of what? X over 3 plus c. So 1 over a, arctan of u over a is the formula we're using, right? But the variable for us is x, and a for us is 3. Okay, so do you all agree? If we ever see a constant over a quadratic where we don't have an x term and we have addition between them, we're in business. Yeah. All right, how about this one? A constant over an irreducible quadratic. What do I mean by irreducible? Not factorable. So it's not a factorable quadratic. If you look at x squared plus 2x plus 17, you cannot factor that, all right? Now be careful, because if you can factor it, we have a different technique, which we haven't talked about. But if it cannot factor, we can still do it, all right? So the way we do it is as follows. So this now that we're at example number 6 here, from here on out, we actually do have to do some work. Like, it's not going to be like, oh, just look, recognize, and crank out the answer. Here, it's just, we can handle this. That's all I'm saying. We can. I don't have to teach you anything new. So here's what we're going to do. We're going to complete the square first on the bottom, all right? So we're going to take x plus, so I'm doing this algebraically. Make sure the coefficient on x squared is 1, which it is, right? And then I'm going to take half of the number in front of x, which is going to be half of 2. So I'm going to take 2 over here. I'm going to divide it by 2. That gives me 1. That's one of my special numbers. And then I take that and square it, right? and that's my second special number. They happen to be the same number in this case. And so what we talked about last class is what you do is you write this down, then you realize a hidden 0 right here, and that hidden 0 is that number added and subtracted. So I add 1, subtract 1, and then what do I still need there? Plus the 17. Okay, now the whole reason we do that is because these first 3 terms are guaranteed to factor, right? Perfect square trinomial. So this turns into x what? Plus 1, that quantity squared. Okay, so that comes off of this number, or you should all be able to factor that. And then what's still out here? Plus 16. Okay, so now let's rewrite the integral. Okay. Now, look at that. Squint your eyes. And do you kind of see a constant over a quadratic plus a number squared? Do y'all kind of see it? So this is formula 17, where u is what? U is the x plus 1, right? And a is 4. Now, the key part of this problem is that expression right here is linear. That's why we can just go straight to formula 17. If you really needed to at this point, like if you didn't see it, you could do a basic u sub. You could let u be x plus 1. And if you do that, you'd rewrite the whole problem and you'd basically turn it into 1 over u squared plus 16 du. But I'm going to try to get us to that point where we can go straight to the answer. So what? 1/4, right? 1 over a, arctangent of x plus 1, right, over 4 plus c. I have just a quick question for you. What if this had been, just what if, okay? That had been a 3 right there in front of the x. Would that change anything? What would I need, Deb? I would have to, what do you mean? I'd have to scale this by 1/3. I'd have to scale it by 1/3 because you'd have to imagine this would be a 3x plus 1. So when you take derivative in here, eventually you're going to get to that 3x plus 1, and it's going to spit a 3 out, and you don't want that, right? So you have to scale by 1/3. Now, it's never going to happen when you start there because you remember your leading coefficient has to be a 1. So that's never going to happen when you do this. Okay? Now, what if we would have had a 3 here to start the problem? We would have factored the 3 out, and then it would have come out of the denominator as a 1/3. So we will never have to deal with that. I just want to keep that theme in your mind that when you have linear expressions, if you ever have numbers in front, you always have to scale that out. So you have to account for it. Any questions here before I erase it? Okay, so if we have a constant over, you don't like it? You don't like this? Okay, it's all right. Constant over linear in business. Constant over repeated linear, we're in business. Constant over quadratic, missing the x term as long as we have addition, we're in business. Constant over irreducible quadratic, we're in business. Okay, here's where things get interesting. How about if we have a linear expression on top and a quadratic on the bottom that's irreducible? Right? What if we have this?
Take a stab at it.
Yeah.
Well, would I complete the square first and then maybe use some?
So if you complete the square, you could probably get there that way. You probably could. I'm going to show you something different.
Okay.
Yeah. So the way I'm going to show this to you, I'm not quite sure if I learned it this way or if I just like figured it out that I wanted to do it this way, but it's the way I wound up, this is the way I teach it. So most likely if you go to the tutoring lab, they're going to do it a little different. And I know the book does it different, okay? So let me do it, and then hopefully I'll explain to you why I like this method, all right? Let me just work through it first, all right? So look, think about it this way. Your denominator is a quadratic expression, right? So if we called the denominator u, right? The derivative of that would be a linear expression. We agree with that? If u is a quadratic, when you take the derivative, the powers on everything come down, right? So you go from quadratic to linear. So what I'm saying is, I'd really like the denominator to be my u, like a basic u substitution, and then I'm hoping that the numerator will be du. But it's not, is it? Let's look at it. So I'm doing a basic u sub.
Yes, it is.
Is it? What's du?
You factor out 8x minus 4.
So it's 8x minus 4
Can you factor out
dx. Oh, wait. Can you factor? Oh, no, it's not going to work, is it? If you factor a 4 out, what are you left with? 2x minus 1. Damn it. We're close, right? Do y'all agree? Like if the numerator, right now, if the numerator was 8x minus 4, then we're there. Do y'all agree? We're there? Because then it's just, you know, what? If the top was 8x minus 4, and the bottom was this, then this is really just going to turn into 1 over u du, isn't it? And what's the antiderivative of 1 over u du? Natural log. So the answer would be just natural log of that, right? Plus c. If this was what it, okay? So it's not though, all right? It's not. But what I'm going to do is I'm going to make the numerator turn into this, all right? So I'm going to get fancy here. I really want 8x minus 4 up top, right? So what I'm going to do first is I'm going to make whatever x I have up there, I'm going to make it turn into an 8x first. So watch the way I do this. I'm going to be clever. I'm sorry? Yeah, I'm going to multiply by 1. I'm going to multiply by 1, but it's going to be 8 over 8. Okay, so imagine doing 8 over 8 out here. That's a 1, isn't it? Now pass the 8 through the numerator and leave the 8 on the denominator outside. Okay, and let's see what happens. We have 1/8 on the outside, integral 8x minus what? Minus 8, right? Shit, we're not there. Right, we're not there? But we're closer, aren't we? We at least have the 8x. Okay? Now, what else did we want it to be? Minus 4. Yes, James?
Are we going to do an 8x minus 4 minus 4?
We could, because that number, you could look at 8, minus 8 as minus 4 minus 4. In this problem, it works out nice, doesn't it? But as a general technique, I'm going to just present it in a slightly different way. What I'm going to say is this. We want minus 4, right? So we're going to make it happen by seeing a hidden 0 again. All right? And my hidden 0 is right after that 8x. Right after that 8x is a minus 4 plus 4. Okay? Just stick with me here, all right? Minus 4 plus 4. 8x, I'll do it in a different color. Minus 4 plus 4. Why did I do the minus 4 before the plus 4? Because whenever we do completing the square, I said always put plus then minus, right? Didn't I say that when completing the square? But here I did the minus before the plus. Why? Because I want minus 4, right? I want minus 4, so I put the minus 4 before the plus. So everyone agrees that's a 0. I haven't changed the problem? No? Okay, but what do I still have up here? Minus 8. Okay. And then all over 4x squared minus 4x plus 3 dx. All right. Let's take a look at what the next line's going to be. I have 1/8 integral 8x minus 4 and then minus 4 over 4x squared minus 4x plus 3 dx. So all I did is I left those two, right, and then I put those two together, which is what James was saying earlier. Like, couldn't we just see the minus 8 as minus 4 minus 4? Yes, but had this been like minus 3, then it would have been a little harder for us to see, maybe, okay? Okay, y'all with me there? We still can't do this. We still can't do this because this doesn't match the top, does it? It doesn't match it. We do have 8x minus 4, but we have a minus 4 next to the minus 4. But that's okay, because what I'm going to do now is I'm going to split this into two integrals. I'm going to do this stuff over the bottom and then this over the bottom. Okay? So now I go to two integrals. I'll do that below this. So my first integral looks like this. 1/8 8x minus 4 over 4x squared minus 4x plus 3 dx. And then my next integral plus 1/8, and then what's on top there? Negative 4. That will come out. I will pull that out. Okay, but I'm just going to write it for this next line. Okay. So that's where we are now, right? Let's discuss this. Have we achieved anything here? This first one we can do, right? This is just natural log. We said if it looked like this to begin with, that's just natural log of the denominator. 1/8 times it. We're in business, yes? What about this one, though? What are you looking at there? A what over what? A constant over an irreducible quadratic, which was the example we did just before this. We know how to deal with these. How do we deal with these? We complete the square on the bottom. So the problem we just did before is now just a part of this problem now, yeah? So here's what I'm going to do. I'm going to go ahead and get to the answer on this one. This one is 1/8 natural log absolute value of 4x squared minus 4x plus 3. Okay, and then I'm going to have a plus c at the very end. So I'm just going to do that. And then I'm going to do minus 1/2 integral 1 over 4x squared minus 4x plus 3 dx. These problems are going to be long, all right? So just get used to that. Are there questions on this? Again, this technique is a little bit different than the book does and a little different than what you see in tutoring lab. And I'm not going to even argue that this is more efficient, okay? I'm thinking that the methods you might see from a tutor might even be a little faster. But I think there's something very valuable in this, and that what you're doing is you're manipulating your expression and forcing it to do what you need it to do. And I think that that's an elevated skill as opposed to just following some formula, if that makes sense. You're trying to force something to happen that isn't naturally happening for you. So you make it happen, right? And it goes back again to that whole hidden zero thing. I really think that that's, again, an advanced sort of concept in mathematics. All right, so I'm focusing all of my attention now on this piece right here. All right? I will come back. I'm going to get an answer there. I'm going to plug it back in after I'm done. Okay, so this is going to be separate work. So right now, I'm trying to find the antiderivative 1 over 4x squared minus 4x plus 3 dx. Now, I'm going to complete the square on the bottom, right? So I have to get a coefficient of 1 here. So I've got to factor a 4 out of everything. So let me start the algebra here. 4 comes out. I have x squared minus 1 plus 3/4. Okay. And now I can complete the square, can't I? And are y'all okay? Well, no, I'll just leave it. Okay, so 4's here. All right, we take the number in front of this, -1, right? We take half of it. That's the first magic number, then we square it, right? And that gives you 1/4. And that's our second magic number. So my next line is going to be x squared minus x. Here comes the hidden 0, which is plus 1/4 minus 1/4. Yes? What do I still have here? Plus 3/4. All right. These first three terms are guaranteed to factor, right? So let's keep track of our parentheses. We have a 4 parentheses, and then these three terms turn into something squared. It'll be x minus 1/2. And that comes from our first magic number. And then what's still over here? 1/2, right? 2/4, which turns into 1/2. So we put those two together, we just get a half. All right. Not so bad, I don't think. Okay, let's continue. I'm going to go back to this integral here, and I'm going to rewrite it. Now remember the 4 came out, right? Of the bottom. So I'm going to pull that as 1/4 outside that integral, and then inside I have 1 over, and then I have this thing, x minus 1/2 squared plus 1/2 dx. And if you now squint your eyes just properly, that should look like formula 17 to you. Right? You've got something that looks like 1 over u squared. U is linear. It has a 1 in front, so we're not worried about scaling. So this is like 1 over u squared plus a squared. But hold on, what is...
What about your 4?
Pardon? The 4 came out of the integral on the bottom out here.
Yeah, that's what I'm asking.
What, the what?
Because we have this negative 1/2 here.
Oh, I haven't even... Everything that's circled in black is what I'm doing.
Oh.
I'm going to take everything in black and stick it back in here, and there will be a negative 1/2 in front of it. Okay? So I'm going to come back to this answer. This is all scratch work I'm doing on the side. Okay? So, yes? We're good to go? What's a, though? You have to be a little careful with a is. It's the square root of this number, right? So it's the square root of 1/2, which is really the square root of 1 over the square root of 2, which is 1 over root 2, right? Which is also... We could rationalize it, right, if we wanted to. Multiply top and bottom by root 2. I'm not going to, though. I'm going to leave it as 1 over root 2. All right? That's what a is. Okay, here we go. So now we have this. This is equal to 1/4. Okay, now the formula. The formula for this should be 1 over a, right? 1 over a. And this is a, right? So 1 over root 2 should just be root 2, shouldn't it? You reciprocate it. So root 2 arctan of x minus 1/2 over 1 over root 2. There it is. Plus c. The plus c is about to come. Any questions? At the beginning of class, did I promise you today would be fun? I didn't promise that, did I? Okay, I'm sorry. I meant to promise that because I'm delivering. I'm delivering it, right? Yeah, so I think we're ready for our answer here. This now gets replaced. Scott. We were talking the other day, right? And you're saying this is like, it's like puzzles almost, right? This is like this big mind puzzle that you're trying to just unwind everything, right?
Yeah, it kind of is.
Yeah, it kind of is. And if you're one of those people who enjoys puzzles, you know, this type of thing, then you're in the right You're in the right field. But if this sort of stuff just really makes you unhappy and miserable, then you should think about, do you really want to do something like this for the next few years in college, right? I mean, you have to have some joy in this. There has to be some pleasure from this.
I mean, once I know my way around the problem, it's better,
Yeah.
but
But see, the struggle should also make the struggle makes that reward, at the end feel good, right?
yeah.
Okay, so all I'm doing now is I'm replacing, that whole integral, all these constants are coming down, and I'm putting it, James, in front of that negative 1/2. And then arctan of x minus 1/2 over 1 over root 2 plus c. And we could do some cleaning up here, couldn't we? Like we could do like root 2 over 8. Even this, I might reciprocate that and just put like a root 2 in front of the x and a root 2 on top of the 2. But I mean, that's correct. I mean, we're there. Wow, so quite a bit of a struggle there, wasn't it? When you have just a general linear expression sitting on top of an irreducible quadratic, you got to do some work, right? You got to do some work. You're going to let u be the bottom. You're going to take a look at its derivative. You're going to force the numerator to become the derivative. And then every time you do that, you're going to wind up splitting it up. And one of them's easy, and the other one is going to be completing the square. And that's the way it would work every time. All right? Unless you get lucky, and in the very beginning it said 8x minus 4. Right? Then you would have just been right there at the answer. So what could possibly be next? What's that?
It's a bunch of voodoo right there.
Shall we look at it the other way? Shall we look at it the way the tutoring lab might do it? Actually, haven't even done it like that in probably 20 years. But we can try it. Don't want to confuse you, or maybe if we have time at the end. What's that? The question is, I showed you the way I like to do these problems, but there's another way you can do it that might be more efficient, but it's less abstract thinking. I'm happy to show that to you all, but I don't want to confuse you all either. How about this? If we have at the end time, I can come back and hit this, which means we're not going to see it because we're not going to have enough time.
Post it on a video.
Yeah, I could. All right, so how about this? What if we have a linear expression up top, and this time a repeated irreducible quadratic? Well, why don't we just try and play the same game? Okay, let's see what happens if we play the same game. And what was the game we played on the previous problem?
See if you can reduce it by taking x squared plus 1.
X squared plus 1 to be the u, right? So let's try that. What happens if we let the x squared plus 1 be the u? Then du would be what?
2x dx.
2x dx. All right. We don't have 2x dx up top, do we? Do we? We don't, do we? So since we don't, right? Since we don't, let's try and make the top look like the bottom. I'm sorry, let's make the top look like the denominator. The derivative. So let's make the top 2x, right? Okay, so to do that, I'm going to have to multiply by what out front? 2 over 2. And then let's pass the 2 just through the top, which will leave us with a half out on the bottom. And we get 2x plus 2 on top, and then over, and then what? The x squared plus 1, that quantity squared, dx. All right, now at this point, we would realize the hidden 0. But what are we trying to get next? What are we trying to get? 2x by itself, right? And we actually have 2x by itself, right? We can just split this up into 2 right now. Just split it.
Yeah.
So we could do 1/2 2x over x squared plus 1 squared dx. And then I'm running out of room here. What would my next integral be?
2 over then?
Plus what happened?
Plus
Just do that.
a half integral of 2 over x squared plus 1 squared dx. Right, so I'm just splitting this up into 2 integrals, this over this, and 1/2 out in front of both. Okay. What about this first one here?
Just 1 over u.
This is like 1 over u squared, right? Because we have a squared there. So that's what's different from the previous problem. It's not natural log this time. It's going to be, well, we'll have to figure it out. And we have a 1/2 out front, right? So this is a basic u sub on this one. So let me put the 1/2 here. And then what will come next? If I let this be u, we said this would be 1 over u squared, so the antiderivative of that would be negative u to the negative 1. So I'm going to write that as negative u to the negative 1. So that takes care of this integral. Doing a u sub on this, right? U is x squared plus 1. So that turns into 1 over u squared du. And I still have 1/2 here. This is u to the negative 2. Antiderivative, negative u to the negative 1. Okay. This one we still haven't taken care of. So let's see. Next to this we have plus integral 1 over x squared plus 1 squared dx. Y'all are gonna hate me. God, I wish that squared wasn't there. That squared wasn't there, it'd be arctan. What now?
Would you want to go ahead and expand that?
Multiply it all out. If we did that, we would have a 4th degree polynomial on the bottom and a constant on top. And not quite sure what we would do with that.
What about just making them next?
What's that? Dad? What do you mean?
Like square root the bottom and the top and then
Oh, at the same time. Okay, so I'm glad you mentioned that. So it would be really nice if we could do like the square root of the top and bottom, right? Because we do the square root of the top, it's 1. Do the square root of the bottom, it's gone. But if that's basically like taking the square root of the integrand, which changes what it is. Like the function is not the same. We can multiply by a 1 out front because multiplying by 1 doesn't change anything, right? But if it's like this. If I ask you to look at this 4, and everyone's like, oh yeah, that's 4, and then you come in here and take square root, that's no longer 4. We're trying to find the antiderivative of this function. If we take the square root of it, it's no longer the function that we were originally looking at. The only way you could do that is if you took the square root and then squared that. Does that make sense? I think students want to do that because you've done it when you're solving equations, like you'll take the square root of both sides, and that's legal, but here we don't have both sides. We have an expression. Yes? Could we multiply by 2x on the top and bottom? No. And the reason why is because It has a variable in it. You can only multiply by a constant. It's still 1, but you can't move expressions with x in and out of an integral. Boy, I wish we could, but we can't. Integration by parts, I don't know if that'll go by parts. I don't see what we'd use in our box. I don't know what would be the u and what would be the dv. Multiply it all out? Yeah, I think we're going to wind up with a 4th degree polynomial on the bottom, and I'm not sure what we would do with that.
Didn't you separate the...
Just like x. Okay, so, all right, so like this. Is that what you're saying?
Yeah.
And then do like 2 arctans? Can't do that. Can't do that. If it were plus, yes, we could, but it's multiplication, so you cannot do them individually. Gosh, that would be nice. I still see people doing it though on some of the quizzes and exams. I think when you're in like the heat of the battle doing a problem, sometimes you forget you can't do them like that unless there's a plus or minus there.
Use trig sub.
Trig sub, that's it. It's trig sub. Wait a minute, I don't see a root. There's a root. I told you were going to hate me. All right, so look, I'm just the messenger. To the 4th power. There we go. Okay, now we ran out of, the reason we ran out of options here is because there was no basic u sub anymore, right? You couldn't let u be x squared plus 1 because derivative of that's 2x, we don't have it. You can't really expand it because then you're going to have a constant over this 4th degree polynomial. What the hell do we do with that? Integration by parts, I didn't see a path that way. But this is legitimate, and you have to recognize that this looks like one of the forms we have. X squared plus a squared, right? X squared plus a squared. We didn't have the root unless we massaged it a little bit. Now we do, right? So what's our trig sub?
Tangent.
X is equal to a tan theta. A is 1, so tan theta. Okay, dx is secant squared theta d theta. And the square root of x squared plus 1 should turn into secant theta. And now I'm going to go after it. Okay? I'm going to need to, I guess, erase. Maybe I'll just stay up here. I'll stay above this. Okay, this new integral becomes 1 over, what's the square root thing turn into? Secant theta, but it's going to be to the 4th power. So secant to the 4th theta, and
Secant squared theta d theta.
times secant squared theta d theta. I can cancel some secants there. So this is going to be integral 1 over secant squared theta d theta. And Scott, that's the one we were doing today earlier. That is just cosine squared. Theta d theta. And how do we do even powers of cosine? Yeah, the power reducing formula, right? So this now becomes, a half comes out, integral 1 plus cosine 2 theta d theta. And that's 1/2. Let's see, now we can take an antiderivative. So theta plus 1/2 sine 2 theta. We have to scale that half, right? That half came from that 2 in here. That's,
Doesn't that turn into? Yes, it
Sine theta times cosine theta.
yeah, so we'll be able to get theta off of this, just doing like an arctan. But to figure out what sine 2 theta is, you saw this in your homework for 6.2. We have to use the double angle identity and turn sine 2 theta into 2 sine theta cosine theta. So I'll do that on the next step. 1/2 theta plus 1/2 times 2 sine theta cosine theta. And the half and the 2 are going to go away. Now, let's get all the information we need. We need to know what sine and cosine of theta are. Here's what we know about theta. Tangent of theta is x. So this is our triangle time. Theta, let's see, x here and 1 here. Because we're going to look at that x as being a fraction, x over 1, opposite over adjacent, opposite over adjacent. And I can solve for the hypotenuse. And that appears, that is something we had earlier, right? And what about theta? What's theta? We just have to take arctan on both sides. Okay. I think we're ready to finish this up. So over here, back to our answer. This right here I'm going to clean up. This is going to be -1 over 2 times x squared plus 1 to the -1. Okay, that's this just rewritten. Negative right here? Oh, I put negative here. I don't even, yeah, that's stupid. Okay, so that drops down. And then this becomes this right here, right? With everything appropriately plugged in. So I'm going to put here plus, okay, 1/2, parentheses, theta, which you said was arctan of x. Okay, plus, now the 2's and the half canceled out, sine theta, which is this over this. So x over square root of x squared plus 1. And then times cosine theta, which is this over this. So times 1 over square root of x squared plus 1. Plus c. We haven't started partial fractions yet. Okay, we're just getting the preliminary stuff out of the way here. Partial fractions, what we're going to be doing is just some stuff we did in college algebra to get us to the point where our integrals look like one of these things we're talking about. And then we can handle each one of them individually. So we might have a partial fraction problem where it breaks down into 3 different integrals where they look like some of the ones we've done here. Yeah.
X over x squared plus 1.
Yeah, so I'm going to clean this up. So this is going to be -1/2 or 1 over 2 x squared plus 1. And then we have plus 1/2 of arctangent of x. And then here we have another half. But this time I'm going to put these together. So x on top. And on the bottom, we have these roots go together, right? And the roots cancel out, so we just get x squared plus 1, and then we still have a 2 on the bottom. So 2x squared plus 1 plus c. Hey, we've got a common denominator there between the first one and the second one, don't we?
Yeah.
We could put those together, couldn't we?
Yep.
We could put these two together. I'm going to write it this way. X minus 1 over 2 times x squared plus 1 plus 1/2 of arctangent of x plus c. There we go. I'm happy with that. We could check, yeah? Y'all feel like checking this one?
No, hold on.
I'm gonna hit the I believe button.
You believe you're at that point? I feel like checking it. Let's just start to check and see what happens. Just a quick quotient rule on this, right? Derivative of the top is just 1 times the bottom minus derivative of the bottom. What's derivative of the bottom? 2 comes for the ride. Derivative of that? 2x, so 4x times the top all over the bottom squared. Okay, plus 1/2, what's the derivative of arctangent of x? I'll put it in parentheses like that. Okay, so we can get a common denominator between those two, can't we?
Squaring the second one.
Right, I need this to be squared, right? So I need to put another one of these on the top and bottom. And I also need a 2 and 2 to turn that into a 4 to match the denominator over there. Y'all see what I'm doing? Okay, let's put it together. Let's see. My new denominator is the common denominator, which is 4x squared plus 1 squared, right? That's my common. And then this right here, I'm going to go ahead and just expand this out. So that's 2x squared plus 2 minus 4x squared plus 4. And then what comes from the other? Plus 2 plus 2x squared.
Minus 4x squared plus 4x.
What am I missing? Plus 4x right here, right? Is that what I'm missing? Yeah, that's okay. But everything else goes away, right? So what do we have on top? What's left on top? 4x plus 4 over 4 times x squared plus 1 squared. And then we can factor 4 out of the top, and it cancels with this 4. And that'll turn to 1. So x plus 1 over x squared plus 1 squared. Worked. All right, let's see what's next. Okay, now we're ready for partial fractions.
Last questions on the test.
So let me give you a little good news. Okay, so the good news is after we get through this, after exam 2, what we're going to be doing is we're going to do applications of integration. So we're going to start talking about areas between curves and all these different things. And if you look in the book, well, forget the book. On the test, exam 3, what you're going to be tested on is setting up integrals. You'll be asked to evaluate a few, like actually compute, like go through the work. But on exam 3, most of it's going to be set the integral up. If you set the integral up correctly, that's the challenging part, the actual integration doesn't need to be done. And that's because we do get to a point where we're like, look, we do have technology, and we could always just type this in and get the answer, all right? So it's kind of like we'll be done suffering through integration. Now, you'll need integration as you move on to take differential equations and engineering analysis. Like, it's never going to go away completely, but in this class, all this really complicated stuff will that'll be like, am I making sense? We're going to get to the integral and stop on exam 3. All right, so that's good news. You don't have to carry it all out. All right, so I think we should start. Deep breath. We only have 20 minutes. Let's at least get it going. So back in college algebra, we talked about what are called rational functions. And a rational function was simply the ratio of two polynomials. So we define a function, f of x, to be some p of x, which is a polynomial, divided by some other polynomial, q of x. And we do have a restriction that q of x can't be 0. If q of x is 0, of course, division by 0 is undefined. So examples of rational functions, here's some, all right? So this first one, right, that's a rational function. Polynomial over